Okay, everybody. I think I can start. First of all, I think I must maybe clarify, I don't know, because this is supposed to be a lecture. So this is not a scientific talk. I will not be talking about my work most of the time. I only may perhaps in a few examples. I think the idea here is to introduce particularly the students in free energy, in the concepts of free energy calculations. I think this will be useful for the students for this afternoon's workshop and for understanding a little bit better many of the talks and lectures that we are going to have along the week. So I will start with very fundamental stuff and try to give a broad perspective of what are free energy calculation methods. And since this is not a scientific talk, I already warn you that you should not wait me end this lecture to ask questions. This is supposed to be a class. So if you don't understand anything, this is particularly thought for the students. So if you if you have some doubt, you will have to stop me and ask things. And the other thing is that I'm not I'm not an expert on this, a particular expert on this subject. I'm not a developer of these methods, and we have other people here which understand these methods better than me. For example, Jim, probably Mauricio. I know that he knows a lot of this stuff. So if you have some particularly advanced question, I would be glad if at the moment some student asks some questions that Jim and Mauricio and Munir and Lucas, I don't know, they pay attention for the questions, because it's very likely that I don't know how to answer it, so maybe they can answer that. So this is supposed to be a class. So I ask particularly for the students to pay attention to this. I think that this will be useful particularly for you. So I hope you like it. I don't think I'm very well positioned here. Bring it. No. So we are going to talk about free energy calculation methods, and I will start in a very fundamental way. We're talking about what are free energy differences. So what are free energy differences? The most simple and most fundamental way, or most fundamental, the moment in our scientific background in which we see free energy difference for the first time is when we study equilibrium constants. And we learned there in general chemistry courses that the free energy difference between two states is related to the equilibrium constant by this formula. And when we look to what this means that the free energy difference is simply the logarithm of the concentration rate of two species that are present in solution. So if we think, that would be very nice. Thank you. Okay, we are only going forward because the backward button doesn't work. So we started bad. I was trying it, so okay. So if we look at this concentration rate, this concentration rate, this means that in other words, that if we randomly pick a molecule from the solution we are studying, if the concentration of B is the double of the concentration of A, if we randomly pick a molecule from the solution, we will have a probability of picking a molecule of B, which is the double of the probability of picking a molecule of A. So therefore, the rate of concentrations in which we use to compute the difference in free energy between these two states, these two molecules, is the same thing as the ratio of the probabilities of finding each of these two molecules in solution. So when we are computing free energies, we are actually computing the relative probability of finding two different states in the system, or two different molecules in the systems. In the system. So the free energy is simply a measure of the relative probability of finding two different molecules in the system, or two different states in the system. In equilibrium, this means the probability of finding, the relative probability of finding these two states means that we call this the relative thermodynamic stability of these two states. So if one state has the double of the stability of the other state, we have a relative probability of finding it in the system which is larger, and that means a lower free energy because of this negative sign for the state of highest probability. Very well. So there should be no problem in computing these free energy differences between two states, because what we would need to do is to, given our system of interest, we should only be, it should only be necessary to do a simulation, and this simulation, we run this simulation for this system, and the simulation must be done in such a way to allow the conversion between the two systems of the two states of interest. And if the simulation is good enough, you observe in the simulation, like you observe in a solution where you are measuring the equilibrium constant. If the simulation is good enough, you will observe in this simulation the relative probability of finding these two states in the simulation. And then, okay, if you have this relative probability, you can obtain the relative probability of the two states, compute the free energy difference, and there would be no complication in computing the free energies in this sense. Okay? So, what's the problem? No? Why we talk so much about free energy calculation methods in simulations? Because we could do the simulations and obtain the relative probability of two states, and with the relative probability of two states obtain the free energy difference. However, what happens all the time in our simulations is that we do a simulation, and the simulation is, instead of sampling correctly this relative probability of the two states, our simulations sample anything else. Particularly our simulations, if we start the simulation in state A, it is very common, very common in our simulations that we will keep sampling state A forever, and our simulation will show up only state A, 100% probability of this state, 0% probability of this state, and the estimate of the relative probability of the two states is wrong. So the problem is not that we don't know in theory how to compute a free energy from a simulation. The problem is the simulation does not sample in general the correct relative probability of the two states. Okay, so we do a simulation. This is very typical. Our simulation cannot sample the different conformations with the correct probabilities that would connect the two states with their free energies. So we have a practical problem. So the problem is not a theoretical problem on understanding what is the free energy difference. The problem is a practical problem, which is how to solve the issue that the simulations we perform are not able to sample the correct relative probability of the two states we are interested in. So we have a practical problem. We want to study how to solve this practical problem. The obvious way to solve this problem is to simulate much more time. So if our simulation was not able to sample the correct relative probability of these two states, we could simulate much more time, and then with this much longer simulation, we could eventually obtain the relative probability of these two states correctly and compute the free energy difference. However, this is almost never enough, because the time scale of these transitions, of the time scale of the stability of one of these states, it's much higher than anything that we can simulate. So we have to do something else. And what we do? We use tricks to modify the simulations. We are not going to simulate something as a conventional simulation. We have to modify the simulation because a conventional simulation is almost never enough to solve this problem. But these tricks that we use to modify the simulations must be correctable, in the sense that we have to know to compute stuff from the modified simulation in such a way to correct these modifications and obtain the relative probabilities of the states in the simulation that was conventional. I mean, we have to be able to correct the tricks we have introduced in the simulation in such a way to obtain the properties of the original system. So the concepts we will be talking about are thermodynamic integration, free energy perturbation, and general biased sampling simulations. And these are three ways which are interconnected with each other in particular cases and in practice, but the general aspects of these three strategies are different, and we'll be talking about these three different ways of modifying the simulations to compute the relative probabilities of the two states we are interested in. Okay? Very well. So the first one is thermodynamic integration. We'll do some formulas, but please stop me if you are not following, particularly because since I'm speaking in English, maybe the emphasis of stuff is not good enough. So in thermodynamic integration, we are thinking about this problem. We have, for example, a conformational transformation in which this might be the movement of a side chain of an amino acid or anything else. And we call a subset of these movements, we call them the microstate A. We say that a subset of these movements is state A of our simulation. We call another subset of these conformations state B. And of course, we have all the movements that are possible for this side chain, for example, and this will be the set of all possible movements that the side chain might have. So we know from statistical thermodynamics that the probability of one microstate is the sum over all all conformations which are compatible with this microstate A of the exponential of the energy of these states. Okay? So the probability of this microstate A is the sum over all conformations. This is a sum over all conformations compatible with the microstate A of the exponential of the energy divided by the partition function. The partition function is the sum over all microstates of this same energy. So we define here the free energy of state A as minus kT, the logarithm of the probability of state A over divided by the probability of observing anything. The probability of observing anything is 1. So this is just a definition that we will use along the talk. So the free energy of state A will be defined as minus kT, the logarithm of the probability of state A, and the probability of state A, we must always recall that is the sum over microstates of the exponential of the energy of these states. I will simplify a little bit. Don't worry about this. This is simple, but don't worry about the operations. Simply, simply to say that when the potential energy and the kinetic energy are a sum or are separable, it's easy to show that we can forget about the kinetic energies and compute only potential energies. Okay, so we will substitute in this probability of state A, we will substitute the energies by the potential energies, and this is how we will be talking about the probabilities of states along the talk. Okay, so this is the fundamental formula for the probability of states in statistical thermodynamics. Oh. I'm ready there. Okay. So very well, if that's the probability, we have to compute the free energy difference. The free energy difference is minus kT, the relative probability of the two states. So then, if we have if we simply substitute the probability of one state in the free energy definition, we have, this is the same formula as before, the free energy of state A is minus kT 1 over the partition function times the sum over all states, all conformations compatible with microstate A of the exponential of the potential energy of these states. And what we will do here, in order to introduce the idea of thermodynamic integration, is to compute the derivative of the free energy relative to the reaction coordinate we are thinking about. So let's go. We are thinking about this reaction coordinate, the transformation of state A in state B. So this is the transformation we are trying to study. So let's just, for in order to simplify the notation, think that this reaction coordinate is very simple. It's simply the movement of one particle along a Cartesian coordinate, or the movement of a particle along the x coordinate. So suppose that our transformation is this particle moving along the x coordinate of the system. Okay, so it's very, very, very simple transformation. The displacement of a particle along a Cartesian coordinate. So the free energy of a particular Cartesian coordinate will be the kT logarithm of 1 over the partition function times the sum over all conformations of the system which are compatible with this particular Cartesian coordinate x1, okay, of the exponential of the potential energy of these conformations. Which is this sum? Okay, if given the position x1 of this particle, all other particles of the system might move. So there are many, many, many conformations of the system which are compatible with the position x1 of this particle. So this is the sum we are performing here. Given the position x1 of the particle, there are many, many, many other conformations which are compatible with the position x1 of the particle. We are summing the exponential of the potential energies of all these conformations. Okay? Are you following me, students? Okay? So now what we are going to do? We are going to derive the free energy relative to the position x1, which is our reaction coordinate. So we are going to perform the derivative of this formula. Here we have a logarithm, so the derivative of this formula is 1 over the argument of the logarithm. There is a minus kT here, times the derivative of the argument, so it's 1 over q times the derivative of the exponential. This is an operation, just believe me, it's correct, it's done correctly. Okay, so this is the derivative of the exponential. When we derive the exponential, there is a minus kT that drops down. This minus kT will cancel with this kT, and there is the derivative of the potential energy relative to x1, which will drop out of this, and there is the partition function here, cancels out with this partition function. What we get at the end is this formula, which is 1 over the sum over all the microstates over 1 over the sum of all conformations which are compatible with the coordinate x1 of the system, of the exponential of the potential energy, times the same thing multiplied by the derivative of the potential energy relative to x1. Okay, this is the derivative of this formula, which is the definition of the free energy for a particular reaction coordinate. Now what we see is that here we have the sum, 1 over the sum over all microstates, and we can put this sum, this 1 over the sum of all microstates into this sum, because this is a constant factor, and then by putting the ratio between the exponential of one particular configuration of the system over the sum over all microstates of the exponential, this is the same definition as we have talked before of the probability of finding a particular coordinate x1, a particular configuration with coordinate x1 within the, I would like to speak in another language, that's because, yeah, you know, look, the probability of a particular conformation of the system is proportional to the exponential of the potential energy of this system, of this configuration. This is statistical thermodynamics. If you have a particular configuration, this particular configuration of the system, position of the atoms, has a potential energy. So the probability of finding this particular configuration is proportional to this potential to the exponential of this potential energy. So the probability of finding this particular configuration in the set of all configurations which belong to the state x1 is the exponential of the exponential of the potential energy of this configuration divided by what is the partition function of state A. And the partition function of this state is the sum over all configurations compatible with the coordinate x1 of the exponential of these potential energies. So when we divide this exponential of the potential energy by this sum, what we get is the probability of observing a particular configuration of the system within the set of all configurations of the system which are compatible with the coordinate x1 which we are studying. Okay? Ask me if not, because the emphasis is very important because in order to understand that. So dividing this by this gets us the probability of finding a particular configuration compatible with state x1, and this is inside the sum, and this is multiplied by the derivative of the potential energy relative to the coordinate x1 for all configurations of the system which are compatible with this coordinate x1. So the sum over all configurations of the system which are compatible with coordinate x1 of the probability of finding this configuration times the derivative of the potential energy relative to this configuration is the average derivative of the potential energy relative to this coordinate, and this average is computed for all configurations which are compatible with which are our configuration of the system which are compatible with this coordinate x1. Okay? So let me see if the next slide is more didactical, or if I can talk a little bit more. So it's okay. So you understand this in a more visual way. What are we doing? So suppose that we want to compute the free energy variation along moving this atom in the x coordinate. So suppose that we fix the position of this atom in coordinate x1 equals 0. So suppose that we fix the coordinate of this atom in a particular x position, for example in the origin, and we start to do a simulation. And the simulation is such that this atom is fixed in this particular Cartesian coordinate. Everything else is moving. Everything else is moving. So for each configuration, it is possible to compute which is the derivative of the potential energy for each configuration of the system, which is everything is moving except the coordinate I have fixed. Everything is moving, but given one configuration of this set of configurations my simulation is sampling, I can compute which is the derivative of the potential energy relative to the movements of this atom which I have fixed. So I can compute the derivative of the potential energy relative to the position which is fixed in my simulation. And I can compute this property for all configurations of my system which are being produced by my simulation. So my simulation fixes this atom in a particular position and everything else is moving. For all particular configuration which is being sampled by this simulation, I can compute the derivative of the potential energy relative to the movements of this atom, and then compute the average of this derivative of the potential energy. And we have shown in the previous slide with those operations that the average derivative of the potential energy relative to the coordinate which I'm interested in is the derivative of the free energy relative to this same configuration. So perform a simulation with fixed coordinate, compute the average derivative of the potential energy relative to the coordinate, and then this will be the derivative of the free energy relative to this coordinate. So a simulation with x1 fixed allows the computation of the derivative of the free energy. So what we do, we perform multiple simulations with fixed values of the reaction coordinate. So we do a simulation in which the reaction coordinate is fixed in a specific value. So this simulation progresses and samples configurations which are compatible with this specific value of the reaction coordinate. And from this simulation, we can compute the derivative of the free energy in this reaction coordinate. Then we do another simulation in which the reaction coordinate is fixed in a different value. So we move our particle in the system, and then we sample all configurations of the system which are compatible with this new reaction coordinate, and then we can compute the derivative of the free energy in this new reaction coordinate. Then we do again the same thing for the atom fixed in a different reaction coordinate along the reaction coordinate I'm trying to study. So I have multiple simulations with the reaction coordinate which I'm interested in fixed in different values, and then I compute the derivative of the free energy along the reaction coordinate, each of these points being the result of a simulation in which I have computed the average derivative of the potential energy relative to a specific configuration. Given the derivative of the free energy along the reaction coordinate, of course, I can integrate this derivative and obtain the free energy profile, except for a constant which will be the reference state which I'm interested in. Okay, so of course in practice you see examples of this probably many people will talk about, but in practice there are technical differences in relative to what I'm talking about, but the general idea is that in thermodynamic integration we perform simulations with fixed values of the reaction coordinate. This is the theoretical idea. So for simulations with fixed values of the reaction coordinate, we are able to compute the derivative of the free energy along this reaction coordinate, and from the derivative of the free energy along the reaction coordinate, we can integrate our derivative to obtain the actual free energy along the reaction coordinate. Okay, do you get the idea? So the fundamental idea is that there is a calculation, an operation, a simple calculation that shows that we can compute the derivative of the free energy from the average derivative of the potential energy along the reaction coordinate for each reaction coordinate. This is the fundamental result that allows us to compute the free energy along the reaction coordinate using simulations in which we fix the reaction coordinate at different values, therefore forcing my system to sample all the values of the reaction coordinate which I'm interested in. Even if my system does not spontaneously go from one state to the other. Now I'm going to fix the reaction coordinate at each of these of the states along this reaction coordinate, and that I will use that simulations with reaction coordinate fixed to recompute the free energy along the reaction coordinate. Okay? This is the general idea of thermodynamic integration. Oops. I think it's interesting to see which are the difference for another free energy calculation method. So remember that we are trying to solve, I would like another slide here. Just going back a little bit. Our goal is to solve the problem, a practical problem, that our simulation does not spontaneously sample all these states. This is the problem. Okay, that our simulation may be trapped here or may be trapped here, and we cannot in a single simulation, because we don't have enough computer time, to sample all the possible states in their correct relative probabilities. We have solved this problem in this case by performing simulation forcing the system to have the reaction coordinate fixed at each of these values. This is how we have solved this problem in this case. And by doing the simulations with fixed reaction coordinates, we are able to compute the derivative of the free energy and then the free energy itself by integrating this derivative. Okay? So now the second general way of doing this kind of simulations, which we call free energy perturbation method. So suppose that we want to do now a transformation. The transformation may be anything, okay, but here suppose it is something relatively simple. So methane being transformed into methanol, for example, or I will be using this notation, I think more than the methane and methanol idea, but I think you want to transform a red ball into a green square in a simulation, and this transformation occurs in water. So which is the idea in free energy perturbation method? So let's go. First, we start a simulation with the red ball in water. So we put our red ball in water, which might be a methane molecule or anything else, and the system will evolve. Naturally, all conformations will be sampled, and so on. The solvent will be moving. And we'll do the simulation long enough in order that we think that the simulation sampled every relevant conformation of the solvent. So there are some configurations which will be very unlikely. For example, if this water molecule is overlapped only on the red ball. This will be very unlikely because the energy of that configuration is very high. Anyway, we think that we have performed a simulation which is very long in such a way that every relevant conformation of the solvent was sampled. Let's believe in that. If that's true, we can get this same simulation. We do not have to perform another simulation, and we substitute the red ball by the green square in our simulation. Simply by that, we get the same simulation, the same set of conformations, and we change the red ball by the green square in our simulation. And since we have sampled every configuration of the solvent, the conformations of the solvent are the same. We have sampled every configuration of the solvent, so there are no different configurations to be sampled because we have changed the red ball by the green square. However, since we have performed this modification in the simulation, the energies of each of these configurations changed. Because we had some interaction of the solvent with the red ball, and now we have a different interaction of this solvent with the green square in each of these configurations of the solvent. So even if the conformations are the same, the probabilities of each of these configurations changed because the interaction of the solute which we are talking about changed in each of these configurations because we changed the solute molecule. However, since we believe every configuration is sampled, we are okay. So we have to recompute which are the relative probabilities of these configurations in the new system in which the solute was changed. Okay? So this is the general idea. We do a simulation with an original molecule. This simulation is long, in such a way that we believe that we have sampled even rare configurations. And then we change this solute by our goal solute, for example, and we recompute all the probabilities in this new set of configurations, because the energies changed when we did this transformation. So what we are doing? So this is the transformation we want to study. We perform a single simulation of the red ball in the solvent, and the probability of each of these configurations, of the probability of state A, which is the red ball, is 1 over the partition function times the sum over all configurations compatible with microstate A of the exponential of the exponential of the energy of these states of state A. State A is the red ball. The relative probability of states A and B is probability of state B over probability of state A is the sum over all configurations compatible with microstate B. Now this would be in principle obtained from a simulation of the green square. These are all configurations compatible with the green square. In principle, one should obtain this from a simulation of the green square. Okay, and this is okay. This is a sum of overall microstate of configurations compatible with the green square of the exponential of the energy of the green square over a sum of all configurations of the red ball, or compatible with the red ball, and of the energy of the red ball in the simulations. However, we are supposing that this simulation of the red ball sampled all configurations of the solvent. Every configuration of the solvent is sampled already in the simulations. In this simulation, so this rate, the sum over all states compatible with the green square, and the sum over all configurations compatible with the red ball are sums over the same thing, because the configurations are the same except for the exchange of the red ball by the green square. So the configurations of all other particles in the system are the same in these two sums. So we can drop this subscript and say we are summing over all configurations of the system. Then we do a trick that in which we multiply on the numerator of this formula this exponential of the energies of B. We multiply it by the exponential of plus the energies of A times the exponential of minus the energy of A. This times this is 1, so we didn't do anything. And then we note that we have this is 1. So we note that this leads us to this formula, which is the sum over all states of the system of the exponential of B times the exponential of positive A, and we have the exponential of minus energy of the red ball divided by the sum over all states of the exponential of the red ball, and this is the same as before. We have a specific configuration with its energy, and this is the sum over all configurations of the exponentials of the energies. This is the probability of finding a specific configuration of the solvent or of the system in the presence of the red ball. This ratio is the probability of finding a specific configuration of the system in the presence of the red ball. Okay, so continuing this calculation, we actually get this. So we have a sum over all configurations of the system. Now I have included here this subscript, which means that I'm summing over all microstates compatible with state A. Because in practice, what we have done is a simulation of state A. So think this is an actual simulation. We are summing over all configurations of my simulation that were produced by my simulation. We are summing the difference in energy, which consists in exchanging the red ball to the green square, times the probability of finding this particular configuration in this simulation of state A. This is a sum over all microstates of the probability times this property. So this is the average of this property in the simulation of state A. So the relative probability of A and B will be the average of this exponential difference of the energies sampled or in a simulation of state A. Okay? I think with examples this becomes even clearer. So what we have done, we are thinking about studying this transformation. This transformation occurs in a particular environment. We do a simulation of the initial state in this particular environment. Then we have a set of configurations of the initial state in this particular environment. We perform our transformation in the same set of configurations. We perform this transformation in the same set of configurations, and we compute the average change in the exponential difference of the energies in the set of configurations. So for each configuration obtained in this initial simulation, we change the red ball by the green square, compute this exponential energy difference, and we average this exponential energy difference along all configurations of our simulation. This is the way to correct the probabilities of the simulation when we perform the transformation of the red ball to the green square. Okay, so we did the simulation of the original state, perform the mutation that we are interested in along all the configurations, and compute this property. The average of this property along all the simulation is the relative probability, the relative probability of these two states in an original simulation. And of course, the free energy difference is simply the minus kt, the logarithm of this relative probability. So the general formula for free energy perturbation is the free energy difference is minus kt times the logarithm of the average exponential difference of energies between the two states studied, and this average is performed in a simulation which is of one of the states only. So in principle, we don't need to perform a simulation of the two states, of the initial and final states. We do a simulation of the initial state and perform the transformation of the initial to the final states in every configuration of the simulation, and the average of the exponential difference of these energies will give us the free energy difference between the two states.
Yeah.
Oi.
So you're assuming here that your final product is just methanol, right?
Yeah, could be anything, yeah.
So maybe in the real case you have some methane state between these.
Oh, let's go. We are going to get there. Of course, we are assuming here that the set of configurations which are sampled by a simulation of the red ball or anything else is enough to represent every configuration of the green square. We did that assumption. So this idea will only be successful if the set of configurations of state A and state B are similar. If these two states are very different from each other, then the mutation will perturb the configurations in such a way that it is very hard in practice to obtain a simulation of the first state that samples correctly the states of the final state. So this is not the general case. So what we do in practice every time. In free energy perturbation, what we do, since we have this formula is only valid if the set of configurations of A and B are similar, we are going to perform this transformation. Instead of performing this transformation at once, we are going to perform the transformation by steps in which each of the steps is small enough such that the approximation of the the approximation thought when computing this formula can be thought to be correct in every of these states, in every of these small transformations that are leading my initial state to my final state by steps. So what we do, instead of studying using free energy perturbation, the transformation red ball to green square at once, we perform a simulation in we will study by steps in which we transform the red ball into a pink rounded square. Then we transform the pink rounded square into a yellow, less rounded square, and then we transform the yellow, less rounded square into a green square at once. So we do now a simulation of the red ball in the solvent or in the environment of the red ball. And instead of transforming the red ball directly into the green square, which would perturb too much my configurations, I transform my red ball into the pink rounded square, which is similar enough with the red ball in such a way that the configurations which were sampled in the simulation of the red ball are a good representation also of the solvent configurations of the pink rounded square. Okay? And then we do this small transformation, and this small transformations allows us the computation of the free energy of this initial transformation. Then we do the same thing, transforming the pink rounded square in the less rounded yellow square, and we perform the calculation of the free energy difference of the second transformation, and so on. And we can divide this transformation in as many steps as necessary, in order that in every step the transformation is subtle enough so that the assumption on the sampling of the conformation is good, and the final free energy difference will be the sum of the free energy differences over all of these intermediary steps. Okay? Wow. Okay. There's no, I'm not obligated to talk everything. So for example, I'll give you an example of that, only very briefly. Suppose that we want to transform in a peptide, we want to transform an alanine to a tyrosine, for example. These side chains are very dissimilar. They are not very similar to each other. So if we perform a simulation of the alanine residue, certainly the solvent configurations of the which solvate the alanine residue will not be representative of the solvent configurations of the tyrosine residue, because there will be every conformation of the alanine residue sampled in the simulation will have, for instance, water molecules in these positions, and these positions should not have any water molecule in the presence of the tyrosine. So certainly the approximation is bad for a transformation done in one step from here to here. And what we do, what it's done in practice, this is one way of doing free energy perturbation in practice, is to do a simulation in which the potential energy of the system, instead of being computed as the potential energy of the alanine or the potential energy of the tyrosine, the potential energy of the system will be computed as a combination of the interactions of the environment with the alanine and the interactions of the environment with the tyrosine. Which kind of combination? So we define that the new potential energy of the system is a sum of a parameter lambda times the interactions times the potential energy computed with the tyrosine plus 1 minus lambda times the potential energy of the system computed with the alanine. And this parameter lambda will be between 0 and 1, and will be varied between 0 and 1 with steps delta lambda. So what does that mean? That means that the first simulation I perform will have, for example, lambda equals 1. And in this case, lambda equals 1 will mean that the potential energy is identical to the potential energy of system 2. which can be the tyrosine or the alanine or anything else. And okay, that would be exactly a simulation of the alanine, for example. However, I do a step delta lambda. With this delta lambda can be, I don't know, times to 10 to minus 5, or let's say 1% or 0.01. So this delta lambda will, for example, if it is 0.01, that means that a second simulation will be such that we will have 99.99 times V2 plus 0.01 times V1. So the second simulation will have a potential energy which will be a combination of the alanine and the tyrosine, except that this combination is much in favor of the alanine. So you transform the alanine and the tyrosine by making the alanine disappear gradually in the simulation, and the tyrosine will appear gradually in the same simulation, in a set of simulations actually, because for each step delta lambda you are performing a new simulation, and you compute for each step delta lambda this is the equation that results from this. So for each step delta lambda you can compute the free energy difference associated with this small transformation. The first transformation being transforming a full alanine into a 99% alanine, 1% tyrosine. The second transformation being transforming a 99% alanine, 1% tyrosine into a 98% alanine, 2% tyrosine, and so on along the 100 steps that will take you from the original to the final state of this you are interested in. So you can compute multiple steps, the free energy difference within each of these multiple steps, and then the total free energy will be the sum over all your steps of the free energy difference of each step. Okay? This is the essential concept of free energy perturbation. So I'll be very brief here. This is an example that Mariana, my student, is working on. She will present something about this on the hands-on in this afternoon. So this is a xylanase, and there are a lot of mutations in this xylanase that increase the thermal stability of this protein. So for example, there is a serine that is mutated into proline, and there is a threonine that is mutated into phenylalanine, and so on. And these mutations increase the thermal stability of the protein, and it's interesting to understand how the thermodynamics of each of these mutations separately, and free energy perturbation is a technique which is adequate for that. I won't enter into detail because otherwise we will take too long time, but what we do is what I was describing. We have to perform these transformations, for example, the transformation alanine to tyrosine in many steps. We have to do that in the folded state and also in the unfolded state of the protein. The unfolded state is modeled by a simple 3-peptide like this one, and then we will have to compute delta G's, which are the free energies computed for each of the transformations performed in the folded state relative to the same free energies computed in the unfolded states, and that allows us to compute which is the gain in free energy for enfolding associated with this mutation. Then this is performed by varying a parameter lambda from 0 to 1 with the steps delta lambda. So this is the parameter lambda. What you are going to get in a typical free FEP simulation is a variation of the free energy as a function of this parameter lambda, and this parameter lambda changing from 0 to 1. And this parameter lambda changing from 0 to 1 means that you are transforming one residue in the other in a very gentle way, such a way that in each step, delta lambda, the approximation that the system samples configurations which are enough to represent the first and the final step of each of these steps delta lambda is good enough such that the free energy perturbation approximation is correct for each of these steps. And this is harder or easier depending on how different are the initial and final steps. and if the initial and final steps are very different, you have to divide these, you have to use steps delta lambda, which are very short, in order that the transformation be very, very, very gentle along all the reaction coordinate. Okay? No doubt? This is the same, it doesn't matter. So now at least we are already almost at lunchtime, but I think we are a little bit late, but anyway. It's okay? Yeah.
The red and the green, the red and the black line is you went back and forth?
Yeah. In this case, it's a good idea to do that. Okay? So in this plot, we have performed generally what we do, it's not mandatory from theory, but it's a good idea in practice. It's a good idea to perform simulations for the reaction in the forward sense. That means transforming this, in this case, threonine into phenylalanine, and do the same calculation performing the transformation in the backward sense. And this is a way to validate the result, because if you get different profiles in each of these directions, it means that you have a sampling problem. Yeah.
Do you mind going back a few slides?
No. Yes, I meant because the which one? Much?
Really bad. There. Finish. It's like you saying, instead of simulating, getting solving configurations in the presence of the red ball, you could have done the same thing, getting solving configurations in the presence of the square.
Yeah, it's exactly the same thing. So I could have done the simulation in the presence of the green square, and then the difference in energy would be B would be A, so this will be minus the same thing, and the result will be the same. It will be the same. So you can do the simulation, you can do these calculations in both directions, and actually one does that in order to validate the quality. Is one of the ways to validate the quality of the calculation we are performing, because they must be, the results must be the same. Okay. Yeah. Go on.
Going forward,
With that I'm okay. Yeah.
What is that anything special about
That.
equals 1/2?
Yeah. This is a technical thing. Is that this was performed with an AMD, and by default in an AMD, this transformation is performed in such a way that the electrostatic interactions are disappeared, and only after the electrostatic interactions are disappeared, the van der Waals interactions are disappeared. So half of this is I don't know which one is which, but half of this is electrostatic interactions being changed, and the other half is the van der Waals interactions being changed.
So
That's because there is a different profile in the kink.
Temper with the van der Waals after tempering with the electrostatic.
Yeah.
For all these
Yeah, there are a lot of technical details in how to perform this in such a way particularly in the extremes, when one molecule needs to start appearing. There are a lot of technical details in how to do that in order to not introduce instabilities in the simulation. But this is not a rule. Other programs don't do this choice of changing the electrostatics then the van der Waals or vice versa. This is not a particular rule of the computations.
Is there?
Yeah. Come on.
Is there any corrections regarding the internal part of the chain residues? Like they have different atoms, for instance.
Yeah. Okay. So this is a good question. That's why you have to, for any calculation of this kind, we have to do the same transformation in the folded state and in the unfolded state, and we have always to compute delta free energy differences, because the internal part is it will be included in this free energy difference, but it doesn't make any physical sense, because in a practical, in reality, you are not disappearing a residue and appearing another residue. In practice, we should have the side chain of one residue leaving the protein to be something physical, and the side chain of the new residue being substituting this residue in the protein also in a physical manner. So the free energy calculation, how it's simply performed this way, does not account by the physical reality of the disappearing or appearing molecule when they are disappeared. You know, so the way to deal with that is to compute delta G's, because we perform these simulations in the folded state, and we perform the same transformation in a non-folded state. And the delta G will take into account this disappearing and appearing of atoms, and they will disappear in the free energy difference. So what we get is the free energy of changing one residue, the difference in free energy of changing one residue for the other in the unfolded state relative to to performing the same mutation, the same changing residues in the folded state. So that's the way to deal with appearing atoms, which the non-physical part of the transformation, by performing delta G's. Okay? So the last set of kinds of tricks that we use to compute free energy differences from simulations, it is what I have called here biased sampling simulations and variations. They have some correlations with the previous methods, but we are going to introduce them in a different way. So our problem is the same problem as always, is that we want to sample the relative probability of these two states, and our simulations keep sampling only state A. So since we don't leave state A in our simulation, we compute a wrong estimate of the relative probabilities of the two states in the simulation. So we want to solve that. And now we are going to solve that in various ways, all of them considering the introduction of external potentials in the simulation in such a way to induce the transformation from one state to the other. So the general idea is that, so we want to transform this conformation into this other conformation. Our simulation does not do that spontaneously. So for example, if I want to sample this point, which is not sampled by the simulation gets trapped here and doesn't even reach this point in my free energy barrier, what I do is to add to my simulation an external potential which has a minimum in this new reaction coordinate which I want to sample. So if I sum now this new potential to my system, the actual potential that's going to be simulated is the sum of the red curve with the blue curve, which is this black curve. Now my new simulation will be trapped here, not anymore in this basin, but in this new basin, which is the basin that is introduced by adding this new potential to the simulation. So I will perform a simulation in the biased potential. In the biased potential, meaning I will perform a simulation in this black potential, which is not the original potential. It's a potential which was deformed by the introduction of this external potential. And how can this be useful? This can be useful if we know how to, given the sampling of this simulation which was perturbed, if we know how to fix this perturbation and compute the original probabilities without the perturbation from the perturbed simulation, that will be useful to compute the free energy difference. Let's see how that's done. So, okay. So here we have our simulation. The original probabilities, the original probability of our given reaction coordinate is proportional to the sum over all configurations which belong to this reaction coordinate of the exponential of the potential energy. And now we add to our simulation an external potential for every coordinate for every reaction coordinate. Now the potential is perturbed. We changed the potential in which the simulation will be performed, so the probability of the reaction of each reaction coordinate changes. Changes in such a way it continues to be proportional to the exponential of the potential energy of this reaction coordinate, but the potential energy of this reaction coordinate is now changed by the perturbing factor. So the potential energy changed from V to V plus V prime, and this now results in a different probability of obtaining this reaction coordinate in our system. Since we are summing over every coordinate which is compatible with this particular reaction coordinate, this perturbation is the same for every term of this sum. You see, we are talking about that we are saying that we have introduced it into my simulation an external potential which has a specific value for each of the points along my reaction coordinate. So given the reaction, a specific point in the reaction coordinate, the perturbation is the same. So the exponential of the perturbation can be put out of this sum, because this term is constant for every configuration compatible with the reaction coordinate I'm working with. So this is an operation, believe me. So this this is the sum over all configurations compatible with this reaction coordinate of the exponential of the potential energy, and this is the same sum which is here. So this is proportional to the original probability of this reaction coordinate. So the probability of this reaction coordinate in the perturbed potential is proportional to the perturbation, to the exponential of the perturbation times the probability in the original potential. So if we divide the probabilities in two different reaction coordinates in the new potential, because this is the prime, we'll have this for one of the reaction coordinates over the same thing over the other reaction coordinate, and what we get is that the probabilities in the perturbed potential are equal to the probabilities in the original potential, not perturbed potential, times the exponential of the differences in differences in potential energy introduced by the perturbation. So let's review that. So what we had is a simulation that was not able to sample correctly the configurations. We will introduce in the potential energy of the simulation a perturbation that varies along the reaction coordinate in such a way that and then perform a new simulation, and this new simulation will have different probabilities of each reaction coordinate because of the perturbation, and these new relative probabilities will be related to the original probabilities by the exponential of the perturbation introduced. Then if this relative probability can be transformed into free energies according to the definition of the free energy, and if we do this operation, we get the free energy in the non-perturbed potential is the free energy in the perturbed potential minus the variation in the potential energy introduced. So if one performs a simulation in the biased potential and obtain a good estimate of the relative probabilities in the biased potential, it's possible to compute the non-biased free energy difference. And this is the fundamental result here. So in pictorial terms, so we have now a simulation which was performed in this black potential, which is the sum of the original potential plus the perturbation, which is the black curve. And this simulation performed in the black potential will be trapped in this minima, and will sample coordinates nearby this new minima. This new minimum, which is the new minimum of the free energy in the perturbed potential. This new simulation will be able to sample points which were not sampled at all in the original potential, because these points in the slope of the original potential were not sampled in the original simulation. But now they will be sampled, and we can compute the relative probability of obtaining this reaction coordinate and this reaction coordinate, which are both being sampled in the perturbed potential. Now I do have a sampling of these two reaction coordinates in the perturbed potential, and these two reaction coordinates were not sampled at all in the original potential. So I had no information about the relative probabilities of these two configurations in the original potential. Now I have a perturbed potential in which there is sampling of these two reaction coordinates. I can compute the relative probability of these two reaction coordinates and obtain one of the differences in free energy between two reaction coordinates along my original reaction coordinate. So what do I do is to add this perturbation for a lot of different reaction coordinates along my total reaction coordinate. So if I introduce this first perturbation will allow me to sample the reaction coordinates we are near this minimum. Then I do another simulation in which I perform a perturbation in a different point of the reaction coordinate, and this will allow the sampling of the conformations near this minimum. And then a different perturbation which will allow me the sampling of conformation near this minimum, and so on. If I do this various times in such a way that the sampling overlaps between these different configurations, if I perform these simulations in such a way that every window, every perturbation overlaps with the nearby perturbation, I can compute these free energy differences between vicinal points along all the reaction coordinate, and then obtain the full free energy profile. This is the kind of stuff that's called umbrella sampling, with a lot of other technical details. Okay? Can we get the idea? So in biased sampling, so there are two other techniques that I like to mention here. These are kind of biased sampling techniques. So imagine that we have this transformation. Let's give a huge step towards obtaining the free energy, which would mean, imagine that you have this transformation. This is the free energy profile of the transformation. We have the problem we always have, that the simulation only samples one of the conformations. And let's suppose that we add to the simulation a perturbation which is exactly the opposite of the free energy profile. Let's suppose that we do that. Let's suppose that we know which is this free energy profile, and we add a potential energy to the system which is exactly the opposite of the free energy profile. In that case, the perturbed potential will be flat, totally flat. And if the perturbed potential is totally flat, in the perturbed potential, the free energy difference between every conformation is 0, because there is no free energy difference between any of the conformations. So suppose if I know how to do this, I can simply I know that the free energy difference at the perturbed potential is 0. So the free energy difference of the original potential will be the free energy difference of the perturbed potential minus the perturbation, which is the formula we have already talked about. But in this case, the free energy difference in the perturbed potential is 0 along all the reaction coordinate, and then this means that the free energy difference is minus the perturbation introduced. So if I knew the free energy profile, it would be easy to add a potential energy which counteracts exactly the free energy profile to obtain a simulation which samples every conformation with the same probability and obtain the free energy difference from the perturbation. Of course, this is not useful at all, because if I knew which was the potential to be added here, I would have no problem, because it was simply a question of computing the free energy differences. So the thing is that I don't know which is this profile. So I have no idea which would be the perturbation that I should introduce in this system in such a way that G becomes constant. In principle, I don't know how to perturb my system in such a way to make all my states in the simulation become equally probable. That's what we're talking about. So how can I do that? I can invent ways to try to do that. So one of the ways to try to do that is, let's think that I start my simulation in the original potential. This is my original potential. And my simulation in the original potential samples only this minimum. And I start my simulation and I observe that my simulation doesn't leave this minimum. And I say, okay, since my simulation does not leave this point, I will add a perturbation in my system at this point to make it move from here. Then I add a small perturbation. In this case, I draw a Gaussian perturbation in this point. And this perturbation will make my system leave this minimum and start to sample, for example, this region or this region, which are now the two minimum of the free energies. Because with this perturbation added, this minimum became less probable, less likely to be sampled, and now the sampling will be majority in this point and this point. So okay, I do a new simulation. I continue my simulation with this perturbed potential, and I observe that my system is now sampling this region, and my system is trapped here, so I will add a perturbation at this point. So I add a perturbation at the new point, which is being preferentially sampled. And now my system will drop from here to here. And then I realize that's happening, and then I add a perturbation here. And I go and I continue adding perturbations to my system at the positions which my system is sampling preferentially. So if my system gets trapped in a position, I will add a perturbation that moves my system from that position. Then it will get trapped elsewhere in a different place, and then I add a perturbation in this new different place. And then it will get trapped in another place, and then I add a perturbation in this place, and so on. And finally, if at some moment I realize that after adding all my perturbations, I realize that the probability of finding any configuration along my reaction coordinate is constant now, so my system starts diffusing along my reaction coordinate perturbed by these multiple perturbations. When I end this process, I know that if the probability is constant along the reaction coordinate, the perturbation I have introduced is the perturbation from which I can compute the free energy difference. Okay? And this kind of simulation is called metadynamics. And it's a kind of, so this is a plot of a bidimensional simulation of metadynamics. You see, the system starts trapped here, then you start perturbing, and then it gets trapped somewhere else, and blah, 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 and so on. And at some point, you have perturbed enough your system in such a way that all the configurations along the reaction coordinate are more or less equally probable, and then you know that the free energy of your system along the reaction coordinate is the opposite of the perturbation that was introduced.
But this moment is exactly when you put the...
Yeah, in principle, then I think people working with these techniques can talk about when to stop better than me. But in principle, you should observe that you have a perturbed potential in such a way that all the configurations along your reaction coordinate are sampled with equal probability. This is in principle. Then probably Jim can talk much better, when to stop a metadynamic simulation. And he will be talking about this stuff. I don't know if you want. Be free to say anything now, or he will be talking about this stuff in order to, because of course, if you really have to wait for that, even the simulation of the perturbed state must be quite long in order to really be sure that you are sampling every state with equal probability.
It takes
yeah.
time to go from one
Yeah, it takes diffusive time to go from one conformation to the other, even in the diffusive regime. So there must be better ways to know when to stop.
Yeah, just briefly,
Yeah.
If you're interested in the free energy difference between the left state and the middle state, you should monitor that as a function of the simulation time, and you normally will see it converge and then fluctuate with some KT or 2 KT value. So this is when the simulation is done. You can monitor the convergence of what you're interested in.
Yeah. But for example, if the transformation is quite long, I think there will be uncertainties on which is the correct moment to stop, because maybe even in the perturbed potential, in the final perturbed potential, it's hard to obtain a good sampling because of the diffusive time of the transformation. I don't know. It might be hard to obtain a good sampling of the transformation even in the diffusive regime, I think, no? Yeah.
You do it stepwise, like let's say from point A to point B in the reaction coordinate.
Yeah, of course.
You do it, let's say between A and B, some intermediary points, so that you do metadynamics at a certain section.
No,
Again at the other section.
it's quite different than, for example, thermodynamic integration or umbrella sampling. In those cases, you're defining where the simulation goes, or indeed placing it in a certain place and running the simulation there. Metadynamics is only saying go somewhere else. It doesn't direct you where to go. It just says go explore, and when you smooth the bias potential, as Leandro said, then eventually you kind of go everywhere with equal probability.
But you could limit this sampling, introducing a potential barrier in order, so it doesn't leave a range of conformations which are the ones you are interested in.
Yeah.
Otherwise, you will start to sampling things you are not interested in. I think that's what you have commented.
If you want to unfold a protein, you want to limit, for example, the radius of gyration, so you don't go to the state when entropy is totally minimized, because this is not physical.
Yeah.
You never go there anyway.
So very nice. So is the idea, the overall idea is clear. So the last thing, so it's an idea which is in some ways similar. Actually, the implementation of this idea is different, but the idea is the fundamental idea is similar, which is that you want to study this transformation. We have the free energy profile. We have the same problem that the simulation doesn't leave this minimum. And we know from our previous considerations that we know that the derivative of the free energy relative to the reaction coordinate is the average potential, the average derivative of the potential energy along the reaction coordinate. And okay, for a simple reaction coordinate, there is a technical detail here, but the derivative of, if the reaction, for example, if the reaction coordinate is a Cartesian coordinate, this is the derivative of the potential energy relative to a Cartesian coordinate. And in that case, the derivative of the potential energy relative to a Cartesian coordinate is minus the force. No? The force is minus the derivative, the gradient of the potential energy. So we note that the average derivative of the potential energy along the reaction coordinate can be associated with minus the force that the system is feeling in this reaction coordinate. Actually, they are essentially the same thing. So we know that we can compute the derivative of the free energy along a reaction coordinate, and if we know how to compute the derivative of the free energy along the reaction coordinate, we could integrate this derivative to obtain the free energy and add this free energy to the original potential to obtain a flat potential. So we are going to understand in the next slide what I'm talking about. So if we had a good estimate of the derivative of the free energy, we can subtract it from the average force. In the previous slide, we are saying that we are obtaining a good estimate of the potential energy and adding perturbations, potential energy perturbations that counteract the potential energy of the system. Now we are saying that if we instead of computing the potential energy, we compute the derivative of the potential energy, we can add to the system not perturbations that are potential energy perturbations. But since the derivative of the potential energy is the force, we can add to the system forces that counteract the forces that the system is feeling in each reaction coordinate. Because of this, so if we get stuck here, I think the next slide is that. So if our simulation is stuck here, but it samples many times this position in this coordinate, this coordinate of the simulation is sampled many times. And since this coordinate is sampled many times, we can obtain a good estimate of the derivative of the potential energy along this reaction coordinate, or which is the same, the force, the average force that the system feels at this reaction coordinate, which is actually being sampled in the original potential. So the system is trapped here. The system is trapped here. So it samples a lot of configurations at this point. So since it samples a lot of configurations at these points, I can compute the derivative of the potential energy along the reaction coordinate at this point. This is a property of this particular point. So I have a lot of configurations which are consistent with position of the atom, with the atom at the origin, for example. So I can compute which is the derivative of the potential energy for movements of the atom in the vicinity of the origin. With this estimate of the derivative of the average derivative of the potential energy, I have the estimate of the average force, which the atom feels at this position. And then instead of adding a potential energy that moves the atom from here, I can add this average force, which was estimated, to the propagation of my equations of movement. So I propagate my equations of movement like in this formula. The position at an atom at a subsequent point in time, a sequence step in time, is the original position times Vt, V delta T, times 1 over the mass, force, this is the acceleration, the force times delta T squared, for example, a simple way to propagate the positions. And instead of propagating the positions in the original force, I propagate the positions in the original force minus the average force that was estimated from this. So what I change in my simulation is not adding explicitly a new potential. What I change in my simulation is adding to the propagation of the equations of motions minus the average force of the points which I have already sampled. So if the minus the average force is well estimated, and this can be well estimated whenever your simulation doesn't leave this minimum, for example, I can have a good estimate of the average force at this point because my simulation doesn't leave this point. The average if this minus average force is well estimated, at some point I will add at every point along the reaction coordinate an average force to the propagation for my trajectory, which will counter-interact the forces that are actually acting in the system. So if the average force is well estimated for every position along my reaction coordinate, there will be no acceleration, there will be no average acceleration anymore in my system, because the average force is being subtracted from the instant force at every time. So the displacement will become diffusive, also diffusive along the reaction coordinate, and the integral of the added force, because the added force is the derivative of the free energy, the integral of the added force will be the free energy profile. The idea is similar to the idea that we have talked before. Similar to method dynamics in such a way that we use the fact that we are sampling a particular region of the phase space. We are trapped there, and we notice that we are trapped there. And in method dynamics, we add a potential energy to the system to leave this point where I'm trapped on, where I'm trapped in. However, in this case, I take advantage from the fact that I'm trapped in this position to compute the average force that the system is feeling along the reaction coordinate at this position. And instead of adding a potential energy, I add minus the average force to the propagation of the trajectory, and that will also provide me a way to escape from this basing of free energy. Then I have to integrate this average force to obtain the free energy profile. This is the kind of technique which is called adaptive biasing forces simulations. I think it's okay, no? There are more stuff to say, but I don't think we can go much further for today. Yeah.
How do you compute the average for every reaction coordinate?
So, you do it on the flight, because you start your simulation, and your simulation will be trapped here. So, since your simulation is trapped here, you are passing. For example, for a reaction coordinate equals 1.5, let's say, you are trapped in the vicinities of this reaction coordinate. So what you are actually doing is sampling a lot of conformations of the system which are consistent with this reaction coordinate. For each configuration you are sampling, you can compute the derivative of the potential energy along the reaction coordinate and accumulate that value. You can accumulate that. And accumulate that, and accumulate that, because you are not leaving this point. At some point, you get satisfied with your estimate of the derivative of the potential energy, of the average derivative of the potential energy, because you are not leaving this point. So you are not leaving, and you say, okay, I have already accumulated 1,000 points that are consistent with this reaction coordinate. And I have now an estimate of the average force, which is not changing anymore. So I now add this average force to the propagation of the trajectory. And then that will make me leave this point to any direction, I mean. Yeah, so it will leave the current position. I can do this progressively. I can start adding from the beginning the force, even if it's not well estimated, which is the point there. I will be adding average estimates of the average forces along the reaction coordinate all the time. The point is, at some point, you will notice that the movement is diffusive along the reaction coordinate. It's completely diffusive along the complete reaction coordinate. It's the same problem as noticing that you have an estimate good enough in metadynamics. At some point, your system should be propagating diffusively along the reaction coordinate. And then the average forces don't change anymore. And then the average forces that are introduced to your propagation of the trajectory are the derivative of the free energy, and you can integrate to obtain the free energies. Yes?
So you don't need an integration grid?
Don't need?
Do you need an integration grid?
You need to keep the information of the average for the estimate of the average force along every reaction coordinate. This is the only information you need to store. So you start your simulation your simulation is sampling this region. You have to have a grid of which is the average force at which is the estimate of the average force at each reaction coordinate.
Yeah, that's exactly my point. Do you iterate over each point and then you move forward, or you
no,
just let the system go?
Just let the system go, and you accumulate.
And you accumulate for your grid.
Yeah, for your grid. You just let the system go, and you keep accumulating the average force, the estimates of the average forces for your grid. You then let the system go, let the system go, let the system go, accumulating average forces for every point of your grid. At some point, you will notice that your system is sampling all the complete reaction coordinate with equal probability. In that case, your grid of average forces is the derivative of the free energy. So the convergence problem is the same as in metadynamics. So how to notice that you have a good enough estimate. Okay? I think I'm okay here. Yeah, I will talk another half hour. I think it's okay, everybody's hungry. So So okay, let's. As I say, this should be an introduction to various techniques that I think you are going ultimately to see in one way or another through the week. So we can discuss this in more detail if someone is interested along the week, this afternoon or so on. Okay? I will stop here because there are other things to say more than this, but it's already too late. Okay?
All right, thank you.